Okay, so we're gonna add these two vectors together. So we're gonna get, let's zoom in a little so we have some more room. R1 minus S1 plus R2 minus S2. And then we have R1 plus 3. Let's put the R's and S's next to each other. R1 plus R2 minus S1 minus S2. R1 plus R2, capital R2, I'm losing it, plus 3S, S1 plus 3S2, and last and least, S1 minus S2. So essentially, we want to try and get it into form where we have R1, where we have R minus S, so something minus S plus 3S, negative S. I want to try and get that into that form. So we can do that by combining these terms and factoring out a -1 here. So if we factor out a -1 in this, we get -1 times S1 plus S2. When we zoom in, it gets a little chunky looking. We can group these terms. We can factor out a 3 here. So we get 3 times S1 plus S2. And then for this one, we can factor out a -1. Let's just leave it as a negative sign. Let's do that with both of them. We factor out the -1, we get S1 plus S2. And if we set our regular R equal to R1 plus R2, and our regular S equal to S1 plus S2, we can see if we substitute those in, the R's in, then we end up with this exact situation again. So it is closed under addition. Check. Finally, vector multiplication. Scalar multiplication. So if we take some vector, let's take this vector again. And we multiply that by a constant. We get that equal to C R minus S, C R minus 3S, C negative S. So now we need to see if we still get the same thing if we multiply this through. So CR minus CS, this is another equivalent. CR minus 3CS minus CS. And if we replace R with R, we set R equal to R, we set S equal to CS, we can tell when we plug those in, we're going to get R equals CR, because this is just a real number. So then we can get our original expression, R minus S. And then we replace it here, R minus 3S. We get negative S on the bottom. So we got the same thing. So yes, it is a subspace. All right, next one, E. Let's see if we can do it. the set of vectors whose last component equals 1. What does this mean? Last component equals 1. In R3. So the last component in R3, because all of these are in R3, that's what the question said. We have some x, we have some y, and we have 1 on the bottom. If we plug 0 in here for x and y, let's just write x equals 0, y equals 0. Then we can't get the 0 vector. We get 0, 0, 1, which is not equal to the 0 vector. So it's not closed. It doesn't contain the 0 vector. So no 0 vector. Not a subspace. Because it's not a vector space. It needs to have the 0 vector in order for us to do linear algebra. We can't do linear algebra with something that doesn't have zeros in its subspace. So not a subspace. All right, last, the set of all solutions to the system x, y, y, z, and 2xz. All right, let's see if we can do this one. This one I'm the most skeptical about, but we'll give it a shot, and if it fails, I'd love to hear what you guys did. X, y, y, z, 2xz. How are you even supposed to interpret this? It's said oh, did we skip E? No, this was part of a problem that we're not doing. That doesn't exist. Okay. The set of all vectors where this is true. So, since we have an equivalent expression, xy minus yz equals 2xz, xy minus yz minus 2xz equals 0. All right, let's check zeros first. So we have 3 components, so our vector is x, y, z. If x equals 0, y equals 0, and z equals 0, then this is closed. So we can get to the 0 vector. But let's see, is it closed under addition and multiplication? Under vector addition. So we have this linear system. Is there a way that we could get x, y, and z by themselves? X, y, z. That's essentially what we're looking for, I hope. Well, let's see if we can factor. I mean, we can pull a z out of 2 of them. So we get z negative y minus 2x have xy over here equals 0. if you want to just solve for z in terms of the other two, and kind of narrow it down. Alright, that cancels this. So this is what z equals. What does x equal? Well, let's leave x and y equal to each other, because z captures this relationship. So, since that equals z, we can see if this is a subspace. Forms a subspace. So let's try and add two of them together. Let's just make these all ones. Add them together. Plus something with 2's. x2, y2. Negative x2, y2 divided by y2 minus 2x2. We get x1 plus x2, y1 plus y2. Subscript. We get this monstrosity, which, since they have a common denominator, we can add them together. Negative x1, y1 minus x2, y2, all over negative y2 minus 2x2. If we substitute x equals x1 plus x2 and y equals y1 plus y2, can we, well, the first one, that gets rid of our first one, easy. Gets rid of our second one, easy. Now we need to figure out if we can get this one in that form. So, can we factor out x1 plus x2? Is this terrible math? Is this just the worst math ever? I think it is. That's just disgusting. Well, we can factor out negative 1. We'll have to come back to this one.